So the first speaker of today is V.Ginzburg from Santa Cruz. He will talk about Hamiltonian systems with finitely many periodic orbits.
Hear me all right? Well, the first thing, of course, I'd like to thank the organizers for inviting me to speak here. It's an absolutely beautiful city, and I enjoy it enormously coming here. It's my second visit, and I love it even more than the first one. The project I'm going to talk about is joint work with my former students Eli Kerman and Bashak Gurel in various combinations. And the project itself is an offspring of a slightly different project. So the names first. Namely, in the course of the last few years, we have been able to prove that a Hamiltonian diffeomorphism of a symplectic manifold automatically has infinitely many periodic points regarding of anything. Say it's a result of a Hinton that a Hamiltonian diffeomorphism of a torus has infinitely many periodic orbits. Likewise, according to Franks and Handel, a Hamiltonian diffeomorphism of any surface has infinitely many periodic points unless the surface is the sphere. And so on and so forth. I'm going to give more details on this stuff in a second. But the point is there is a broad class of symplectic manifolds for which infinitely many periodic points exist by default. On the other hand, I mean, all this activity of trying to prove this thing in a greater and greater generality has a natural limit. There are Hamiltonian diffeomorphisms with only finitely many periodic points, and the simplest one is an irrational rotation of a sphere. So take a sphere, take a rotation about the z-axis in some irrational angle, and there are two fixed points. These are the only periodic points. Everything else, well, it's just a rotation of a circle, so in an irrational angle. Now let me give some more details on what we know here and what we don't know. I want to start with setting notation and conventions. So throughout this talk, M to N omega will be a closed symplectic manifold. Phi will be the time one map of a Hamiltonian time-dependent flow, so that's a Hamiltonian diffeomorphism. I will be interested in k periodic points or in periodic points of phi, and when I think in terms of a time-dependent flow, these are also k periodic orbits of the Hamiltonian, so H is a Hamiltonian here. And among those, I will be interested in contractible ones. So when I say a periodic orbit of phi, or a fixed point of phi, or a periodic point of phi, I always mean a point that corresponds to a contractible orbit of H. It's not Hamiltonian. It's symplectic, but not Hamiltonian. So, well, a Hamiltonian diffeomorphism got to have fixed points at least. Now, when it comes to symplectic manifolds, there are a few invariants associated with them which I want to consider. So for a symplectic manifold, the first Chern class is always defined. And when I evaluate the first Chern class on the pi2 of the manifold, I get a subgroup of Z, and the positive generator of this group is called the minimal Chern number. If the group is 0, in other words, if C1 is 0 on pi2, we set n to be infinity. For instance, when the manifold is the projective space of dimension, of complex dimension n, the minimal Chern is equal to n plus 1. The manifold is said to be, so that's one definition I need. The manifold is said to be monotone if omega, the symplectic form, is proportional to the first Chern class on pi2. And the proportionality constant is positive, or at least non-negative. We say negative monotone if the factor lambda here is negative. These are all pretty much standard definitions. And the manifold, that's already for instance, CPN is monotone. Whenever H2 has rank 1, the manifold is necessarily monotone, because on the one-dimensional space there is up to a factor, there is just one linear function. So any two linear functions are necessarily proportional. Well, if both terms here vanish, the manifold is said to be symplectically spherical. Symplectically spherical if C1 on pi2 is equal to omega on pi2 is equal to 0. Finally, when we take omega and start evaluating it on pi2, we get a subgroup of R, and this can be a discrete subgroup or it can be a dense subgroup. So if it is discrete, we take the positive generator of this group, and if it is discrete, we call the manifold rational. Otherwise, it is irrational. And again, if the group is 0, for instance, for symplectically spherical manifold, this rationality constant lambda naught is said to be infinite. So for instance, a monotone manifold is necessarily rational. And the rationality constant lambda naught is equal just to lambda times the minimal Chern. Finally, there is yet one more notion of weakly monotone manifolds, and I'm not going to write it down because we actually don't need the definition. Monotone manifolds are weakly monotone. Now, here is a little table of what we know and what we don't know about the existence of infinitely many periodic points. So that's the state of the art. Let's make this little table. There are 3 classes of manifolds. The manifolds for which you always have infinitely many periodic points. Are all manifolds with C1 on pi 2 equal to 0. So whenever C1 on pi 2 is equal to 0, you necessarily have infinitely many periodic points for any Hamiltonian diffeomorphism. When the manifold is rational, this is a relatively recent result of Gurel and myself without rationality. It is a result of a student of mine, of Doris Hine. It's yet to be written, but I think it's correct. So once C1 is equal to 0, tori, surfaces other than spheres, lots of manifolds, you automatically have infinitely many periodic points, and these manifolds don't belong to the subject of this talk. Then there are manifolds like the sphere, for which we have Hamiltonian diffeomorphisms with finitely many periodic points. And finitely many. Let me describe one source of such diffeomorphisms. So let's say M admits a Hamiltonian torus action. So that's an example. A Hamiltonian torus action with finitely many fixed points. In this example, this would be just, the torus is one-dimensional, it is a circle, and the action is just the rotation about the z-axis. So phi is then a Hamiltonian diffeomorphism generated by a generic element in the torus. Let's get more specific. Let's write down a formula. So let's say we have a CPN with coordinates z0 through zn, the homogeneous coordinates. I will normalize the whole thing so that the sum of squares of the absolute values is equal to 1. So I'm thinking of CPN as the quotient of the sphere, of the unit sphere, by the Hopf vibration. Let's take the Hamiltonian equal to, well, I want to take a positive. I want to take any quadratic form, 0. And the only constraint I have here is that all eigenvalues of the quadratic form are distinct. Then the time 1 map of this Hamiltonian has exactly n plus 1 periodic points. These are the fixed points, and these are the coordinate axes. So this is one class of manifolds we have here. With isolated fixed points. And then everything else, and even though this column is much more narrow than the other two, in fact, it is a much bigger class. It's the class of manifolds for which we don't know. Probably the majority of them in this category, probably these guys are relatively rare. So I want to study something like that. But of course, if all my examples, I want to study Hamiltonian diffeomorphisms with finitely many fixed points. Of course, if all my examples were coming from Hamiltonian torus actions, I think this would not be like a subject of dynamics or symplectic topology. You certainly don't need symplectic topology to study Hamiltonian torus actions. So the question is now if we have other examples. This is actually a non-trivial matter. I asked several people, and eventually, somehow by chance, I asked Katok. So here is continuing the list of examples. There is a construction, very old result of Anosov and Katok, which says the following. There exists a Hamiltonian, well, everything here will be Hamiltonian. So there exists a Hamiltonian diffeomorphism of CP1 of the sphere with exactly 3 ergodic measures. And these 3 ergodic measures, then actually we know what they are. A Hamiltonian diffeomorphism of CP1 of S2 must have 2 fixed points. And then there is the Lebesgue measure, the symplectic form, and nothing else. So in a sense, outside these 2 fixed points, it is uniquely ergodic. There are no, so in particular, there are no periodic orbits there. Now then, of course, one can sort of take products of this thing, and one thing we learn from this, that's a very old thing, by the way. It's something like 70, let's say the 70s, and moreover, it's the early 70s. So one thing we learn from this example that there are things that do not fall in the category of Hamiltonian torus action. So there is something to study here.
This example exists in all dimensions, right?
Now here is a nuance. This example exists in all dimensions, but only as a volume-preserving thing. As a Hamiltonian thing, it's a little bit, so I really had to twist his arms here, and it's pretty much open, although one can hope the following is true. So this is a question, conjecture, or something. And this is a reasonable question. I'll state it probably as a conjecture. There exists, or does there exist a Hamiltonian diffeomorphism from CPN to itself, which is on the one hand ergodic, and on the other hand has exactly n+1 periodic points. These are necessarily then the fixed points. So one cannot expect this sort of minimality. One cannot expect it to have only n+2. One should not probably expect something that strong, but this is a reasonable conjecture.
Did you ask Katok?
Oh, I talked very extensively. It took us a few hours to arrive at this question. So that seems to be a reasonable question. At least it seemed to be. Since then, I thought a little bit about it, and I see some difficulties, but not necessarily great difficulties. All right. So that's sort of the setting of the problem. At least we know what we are studying, and we know that sort of there are interesting objects here to study. Maybe I'll erase now all this stuff. So the main point is that whenever you have a Hamiltonian diffeomorphism with finitely many periodic points, the mean indices of those points and their actions must satisfy certain relations. This is kind of the results of this talk I'm going to, in a nutshell. So let's first of all give a little definition that will just simplify the exposition. We will say that phi from M, again, a Hamiltonian diffeomorphism, is perfect if every periodic point is already a fixed point. A Hamiltonian diffeomorphism with finitely many periodic points can always be turned into a perfect one just by passing two iterations. So you can always iterate it enough times to make every periodic point fixed points, and this just makes stating the results a bit simpler. Sort of periods do not enter the picture, and one can always translate things back. And if I'll just assume that everything is perfect throughout. Then I need one object which is not maybe so well known, and this is the mean index. So let me recall what it is. Well, let's start with a path in the group of symplectic transformation. And I look at its eigenvalues, and among those, I will look at the eigenvalues on the unit circle. Those come in pairs. And there is a canonical way using the symplectic structure to pick one in every pair. And then as t changes, the eigenvalues will sort of move on the unit circle, maybe bifurcate, etc. But let's assume for a second that no new eigenvalues on the unit circle occurs in the process of deformation of this thing. Then every eigenvalue will sweep an angle. And the mean index of the path phi is just the total angle swept by all eigenvalues. So in this example, the mean index is this. If you have two eigenvalues, the white one and the pink one goes here, then the mean index is the sum of this angle and that angle. Now when we have I don't know who introduced the mean index as this sort of rotation number. I know it from the paper, and this is the definition from the paper of the of Salomon and Zender. Now let x of t be a periodic orbit of the Hamiltonian H. And remember, when I say a periodic orbit, I necessarily mean a contractible periodic orbit. So let's take, so that's x. Let's take a disk bounded by x. Let's take, so this is like U, a disk bounded by X. Let's take a trivialization of the tangent bundle to M over the disk. It is essentially unique after homotopy because the disk is contractible. Boris?
Eigenvalues appear in pairs.
What?
Symplectic matrices. The eigenvalues appear in pairs.
I think it's 0. Is it what you're trying to suggest?
You think that you are taking just half?
Well, I'm taking, what I'm doing is, there is a way which I did not describe to pick one in a pair.
But what if they collide? You have to kind of have some
What do you mean they collide?
So you may be tracing just one of the elements of the pair, but they can collide at some point, and then you have choices.
No, the element, what do you mean? No, there is a canonical way to pick one in a pair.
Two pairs can collide.
Yes.
You have some choices after collision. I mean, if you have multiple values, probably.
Of course.
Anyway, there is a way.
There is a way to do it. There is a way to write down the formula. Okay? Just trust me. With this one at least. So let's fix such a disk, and let's fix a trivialization of the tangent bundle over the disk. You know, like if I just try to trivialize the tangent bundle along X, X is a circle. There are tons of trivializations, tons of different trivializations, but a disk is contractible, so there is just one. So let's fix a trivialization. With this trivialization, I can treat the linearization of the flow along the orbit as a path in the group of the symplectic diffeomorphisms. Pardon me, in the symplectic group. So with this trivialization, I can just think of the linearized flow along X as a path of this type. And by definition, I say that the index of X with respect to this trivialization, with respect to this disk, is equal to the mean index of the path. So that's the definition. Now there is an ambiguity here, and the only essential ambiguity is what the only ambiguity that actually affects the result is what happens if I seriously change the disk, the bounding disk. So I can take a disk, so here it is, and I can attach an element of pi2 to it. I can attach a sphere to it. And then the mean index will actually change in a non-trivial but controllable way. Namely, it will change up to the integral twice of the first Chern class over the sphere. So I need to take the first Chern class, which is already appeared here, and integrate it over the sphere. Which says that when now I look at the index mod minimal Chern, it is well defined. Or mod twice minimal Chern, it is well defined. So it is independent of the choice of, we call this disk a capping. It's like a cap attached to the periodic orbit. Which, by the way, tells us that sort of the bigger, the larger the n, the more information we have here. It's good to have a large n. So that's like the first thing I need to use, and now we are in a position to state like the first little theorem. Well, maybe let's before I do it, so let's say the setting. So I have phi from m to m, finitely many periodic perfect. Every periodic point is already a fixed point, and there are finitely many of them. x1 through xm. Let's put, all right, let's say lambda 1 through lambda, pardon me, delta 1 through delta m be the mean indices. Theorem 1. Let's assume that the minimal churn is sufficiently large, at least half of the dimension plus 1. Then the collection of mean indices satisfies a resonance relation of the form an integer times the first one plus the integer times the second one plus an integer times the last one equal to 0 modulo, everything here is modulo twice the minimal churn. So there is a constraint. There is a constraint the minimal indices must, the mean indices must satisfy. Now there is a question. What is this resonance relation? I mean, say given a manifold, CPN, what is it? Well, of course one can do an example. Let's do an example. For CPN, things are very explicit. As usual, we take our Hamiltonian lambda naught. We take a quadratic form. Calculation shows that the mean indices are, to get the first one, I have to take, well, there are like n plus 1 of them. To get the, I don't know, case 1, I take the sum of all eigenvalues other than k and subtract n plus 1 times the case 1. So these are the mean indices. K here ranges from 0 to n. That's a direct calculation. So clearly, depending on the choice of eigenvalues, there can be lots of resonance relations, or few. But there is one resonance relation that holds for sure, regardless of the choice of eigenvalue. Namely, always the sum of the mean indices is equal to 0. When I add these things, there are exactly n plus 1 equations here. When I add them all up, these terms are going exactly to cancel out. Maybe I should have n here. Whichever way, this is true. So I went to kind of this is a talk which has many parts. I sort of got this question, and I went to this and that person. The next person I went to was Yael Karshon, my old-time friend and collaborator, and I asked her whether the same would be true for a general Hamiltonian torus action. And actually it turned out to be a non-trivial question in the sense that it took her a couple of days to produce the answer, and the answer is yes, this is true in general when you have a Hamiltonian torus action. So The second instance when it is always also holds for general torus sections. And then Eli and I also showed that it also holds when there is just one resonance. Well, of course, you know, if there is one resonance, there are many resonances, but resonances form a free abelian group. So saying there is only one resonance is just saying that this group is Z. There is just one resonance generating all other resonances. So this is also true when there is just one resonance. Now, well, I don't know what I'm talking about. So what are the examples in this proposition? That's an interesting question. So there are basically two categories of manifolds you want to work with, either monotone or negative monotone. Well, it's not like it doesn't really exhaust all, but that's a fairly representative class. So for positive monotone, CPN is the only known example. When you think about positive monotone manifolds, the minimal churn tends to be small. For instance, for the Grassmannian, it would go 1 unit down. So this theorem wouldn't apply to the complex Grassmannian. There are lots of negative monotone manifolds, it's a well-known fact, with large minimal churn. However, those hypothetically fall into this middle column. Hypothetically, there we have infinitely many periodic points. So hypothetically, they never satisfy the hypothesis here. But it is just a conjecture. It's probably like years from being proved. So for now, those fit into this category too. So this is to answer this question. You know, it's an easy proof, and I don't want to prove it though. Maybe I have other results to state. So let me just say that this is essentially a Solomon-Zender argument mod. Well, all right, what the hell? Let's prove it. Mod 2n. Let's prove it very quickly. So I will, proving this theorem, I will assume for the sake of simplicity that phi is non-degenerate. It's purely a technical assumption. It's not really needed. It's just easier to talk about phi is non-degenerate, meaning that all fixed points are non-degenerate in the classical sense of dynamical systems. There are no eigenvalues equal to 1. Well, then to every fixed point, we can associate the so-called Conley-Zender index. And it has, and one property of that of the Conley-Zender index is essential for us. It is pretty much a round-up of the mean index. Round up to half of the dimension. Less than n. So it does not deviate from the mean index by more than half of the dimension. Well, now let's, and maybe the second fact I want to mention is that the mean index and the iterations behaves in a very simple way. It's pretty much clear what's going on from this description. When I iterate the picture, I just, keep on adding the total rotation angles. So it's actually homogeneous with respect to iterations. Just by the definition. This is the two facts I need to know at the moment. Now let's take the mean indices and order them and form a vector. Or it's not rather a vector, it is a point in the torus, in the m-dimensional torus, which is just R mod 2 times the minimal churn times z to the m. I can do it for phi, I can do it for all iterations. So delta of phi to the k is equal to k times delta of phi. Now, there should be a non-trivial input in this trivial result, namely Floer theory. Floer theory tells me that there is at least one fixed point with the Conley-Zender index equal to n. Well, just because there is non-trivial Floer homology in degree n, something should generate it, and the Floer complex is generated, roughly speaking, by these guys. Well, now let's see. Let's take a domain pi in this torus. So if I take coordinates theta, such that at least one of the coordinates is not too far away from n. This is a domain in the torus, and the condition that the size of the torus is at least n plus 1 tells us that the domain pi, well, the closure of the domain pi is a proper subset of the torus. So it's not everything. Now, so what do I know? I know that k delta, this collection of points, is necessarily in the domain pi. On the other hand, if there were no resonance relations, it would be dense by the Kronecker theorem. So no resonances implies that k delta is, the sequence is dense. So it cannot be contained in a proper subset. So that's a very easy proof. Interestingly, it's hard to improve on it. It's hard to extract more information, although it might be possible. All right. So that's one class of relations. The second class of relations I want to talk about is a totally different thing. And here again, I need to introduce a new notion. So let me assume that M is monotone or negative monotone. So positive or negative monotone. I recall that, well, I have erased it, that means that omega on pi 2 is equal to the first Chern class on pi 2. The action of a periodic orbit x with a capping u is defined, well, if you, several people yesterday wrote down the formula, we just integrate omega over the capping, over the disk, and add to it the integral of h over x along the orbit. This is, again, something that depends on the capping. However, when I change the capping, it changes in a very similar fashion, except here, instead of the first Chern class, I have to put the symplectic form. So let's take now the symplectic, the action, and subtract lambda times the mean index. This eliminates any ambiguity. This thing is independent of u. When I change u, when I attach a sphere, both terms change in absolutely the same way. So this is a well-defined thing. A very similar invariant has been considered by Palterovich and Salomon, but people would always put the Conley-Zenderi index rather than the mean index. And it's essential for what follows that we have the mean index here. Now we are in a position to state the second theorem. Theorem to this one with Gurel. So I want to, in the interest of saving time, I'm going to skip some cases of the theorem. Let me just sort of, there are other variants of the theorem. Let me just state a couple to give you the idea of what's going on. First of all, let's assume that either n is large or m is one of the following manifolds. I'm going to write down a list. First of all, CPN is still OK. But now I can add things. For instance, I can add complex Grassmannian, something that was not covered by the first theorem due to the minimal Chern requirements. Or it can be certain product of this manifold. When you take a product, sort of the first Chern class relative to the dimension always decreases. So it's actually usually the reduces the ratio of these two, which is kind of makes the torus much smaller. So in all of these cases, the domain pi would be the entire torus. It would not work. Or say a product of CPN and something symplectically spherical. And finally, I will assume that phi is perfect. And there are, as usual, just finitely many fixed points. Then under this condition, we call this guy, this action, augmented action. So, the action augmented by the mean index. I don't know a good name. You can call it the action mean index functional, except it's not a functional. It's defined only on periodic orbits. So let's call it augmented action for the lack of a better name. Then actually, when we look at the augmented actions of these orbits, at least two of them are equal. They cannot be distinct. They cannot be distinct. there is a relation. This time a relation involves both actions and the mean indices. Here is another much more accurate result along this line. So let's say, let's call it theorem 3. This is again with Gurel. Let's say we have a perfect Hamiltonian diffeomorphism of CPN with exactly n plus 1 fixed points. Hypothetically, it's the only possible case. The Arnold conjecture tells us that there must be at least n plus 1 fixed points. And in all known examples, once you have more than n plus 1, you have infinitely many. This is actually a reasonable conjecture. For CP1, for the sphere, it's a known result of Franks and Handel. So even though these are restrictive hypotheses, but it looks like this is the only possible situation when you have something perfect. Then all fixed points have equal augmented actions. So actually, it's not just the two of them are equal. They all are equal to each other. Now, this leads to a very interesting question. All right, so in this situation, we got this number. What is this number? They all are equal to each other, but what are they equal to? When we look at the definition, which I have not erased yet, of course, there is always an ambiguity. We can add a constant to the Hamiltonian. So kind of the question without normalizing the Hamiltonian makes little sense, but there is always a canonical way to normalize the Hamiltonian, saying that it has zero mean for every moment of time. This is like the absolutely standard normalization. So once we normalize it this way, one can ask, one can ask what this number is. In all known examples, it's then 0. For torus sections, it's 0. In Katok's example, in the Anosov-Katok construction, you modify the thing away from the fixed points. So it doesn't really change the mean indices and actions. So you start with 0, you still get 0. Maybe it's always 0. We absolutely have no clue how to prove it. So that's like the first part of my talk. I have 2 more parts to go. So let me get let me try to be brief here, because it's a morning talk. All right, so one can say that, all right, these perfect Hamiltonian diffeomorphisms are, of course, peculiar objects, but my main speciality is the existence of infinitely many periodic points. So let's try to go back to those guys. And here is an immediate application of these theorems. Theorem. Let M be one of the manifolds these theorems apply to, either CPN or a manifold with the large first chain, or the Grassmannian, or one of these guys. Then Hamiltonian diffeomorphisms with well, then the existence of infinitely many periodic points is C infinity generic. So phi with this is a subset in the group of Hamiltonian diffeomorphisms of M. And the assertion is that this subset is C infinity residual. Now here so basically for any of those manifolds, sorry, this is again Burrell and myself. For any of those manifolds, you generically have infinitely many periodic points, and this is as expected because we started sort of with understanding that these perfect Hamiltonian diffeomorphisms are very rare. And that's an example sort of confirming, that's a theorem confirming that feeling. So as usual, I went to experts in dynamical systems with the question whether this result is obvious or not. It is obviously a consequence of the theorems just because any relation is very easy to destroy by a small perturbation. And that's what you do. I mean, it just takes a few lines to prove. So I want to emphasize a couple of things here. First of all, C infinity. C infinity is important. If I replace C infinity by C1, then there is a much more general fact, actually, Hamiltonian diffeomorphisms with a dense set of periodic orbits are generic. This is the closing lemma. But there is a huge difference between C infinity and C1. For instance, the closing lemma holds pretty much regardless of what class you consider. Hamiltonian, symplectic, volume preserving. Whereas here, if I replace Hamiltonian by symplectic, it's simply wrong. So this is essential too. And that's an interpretation of Hermann's non-closing lemma. It's known that the closing lemma breaks down completely in a very bad way when you replace C1 by a greater smoothness. And actually, it breaks down so badly that even this is wrong. Even this theorem breaks down. So that's one thing. Secondly, one can think of it as a global version of Moser's version of the Moser-Berhoff theorem, which says that whenever you have an eigenvalue on the unit circle, whenever you have a Hamiltonian diffeomorphism with a fixed point and an eigenvalue on the unit circle, you generically have infinitely many periodic orbits. So once we can somehow ensure that there is an eigenvalue on the unit circle, the result follows easily from dynamics. However, it appears to be like there is no way in this setting to guarantee that. Here is a little, almost immediate consequence of the Berhoff theorem, which says that if H, the odd dimensional homology of M is non-zero, then the same is true. Trivially here means it's a simple combination of Km of Moser's theorem and of Floer theory, just kind of combining the two theories together, you get this result. Most of the manifolds here do not fit in this category. CP and Grassmannians, they all have odd homology equal to 0. That's one application of the theorem. And the second application, I don't have time to go into. The second application concerns Reb flows. So this is, again, a little theorem with Eli Kerman. And basically it says that when we look at rep flows instead of Hamiltonian diffeomorphisms, there is a very specific resonance relation the mean indices of orbits must satisfy. It's not a linear relation. Maybe I just write it down to give you a sense of what this relation looks like. We break simple orbits into two classes. I would call them good and bad. For each one of them, we take plus minus 1 depending on the orbit. This is a certain function of the orbit. Divide by the mean index of the orbit. This is for the good orbits. For the bad orbits, I'll take again plus minus 1 depending on the orbit, divide by the mean index of the orbit, but take 1/2 of this sum. Here I say I sum up over all simple orbits with positive mean indices. What this turns out to be, it's roughly equal to the earlier characteristic of the contact homology Otto talked about yesterday. So this is what's equal to chi plus of m psi. This is for a rep flow. Psi is the contact structure, and this invariant, Otto considered in his thesis, is something like an asymptotic Euler characteristic. We have to take 1 over n, the sum of ranks of contact homology from, say, 1 to n, average passed to the limit. And this is an invariant of a contact structure, and it can be expressed purely in terms of Reb orbits. What's peculiar here is that this is actually a local, just as ordinary Euler characteristic, it is a local invariant. To calculate it, you don't need to go through the pain of calculating the homology. You can just look at the orbits, look at the local information, local structure of the orbits at the mean indices, add them up, and get a non-trivial topological invariant, which is non-trivial enough to distinguish different contact structures. Of course, it's not as good as the contact homology itself, but it's good enough to distinguish some interesting examples. So for the sphere, when the manifold in question is the sphere, this is the rep case, the Euler characteristic in question is equal to 1/2, and then these results were obtained by Eklund and Hofer and then Viterbo. In the late 80s. So that's kind of a generalized version, a generalization of those results. As just in the same fashion as for Hamiltonian diffeomorphism, we again derive the generic existence of infinitely many Reb orbits. When we apply this to the unit cotangent bundle, to the geodesic flow, we recover the generic existence of infinitely many geodesics. This is like surprisingly recent result going back some maybe 10 years, 10, 15 years, depending how you count, of Hingston and then Rademacher. So that's already a slightly different story. Sort of here it can deviate into contact topology, but I think it's a good time for me to stop. Thank you.